All right. So in this class, we are going to consider the concept of our magnetism. This is the first part that you need actually in your syllabus is you are to consider the magnetism. You need to also understand the concept that happens when you are working with a permanent magnet. Remember, just consider a magnet. What is it that you understand about a magnet? Remember, you'll be having these two poles which affect a magnet, the south and the north. So considering that we have got the magnetic field around this magnet. So we're going to notice or have the magnetic field as we have got this attraction concept, north trying to attract with the south. So we're going to have this part of the magnetic field, which is happening. The same concept, going to have this north to the south and this other way. So these are magnetic field that we are having. So they are trying to have that attraction that as we consider these magnetic fields. These ones that are coming are the ones that we are going to be having entering at this side. So what is the exact concept that we need to understand as we are to consider these magnetic field that are around a permanent magnet? So when you're considering the magnetic lines of flux, which is the magnetic field lines, what are these? All right, let's talk about these first. The magnetic field lines. The magnetic field lines, they also can be referred to as the magnetic lines of flux or the magnetic lines of flux. So it can be given in that manner. So these are the ones that we are seeing in this presentation. So it is simply the area or the region around any magnet. That is what you're talking about. The area or region. This is the area, or you can refer to as a region around any magnet. Around any magnet. So that is the part where we are considering the magnetic field. So this is this field that we are considering. We are now saying it is made up of what? The magnetic flux, which is the magnetic field lines. So we have this as our magnetic field. So as the magnetic field that we are having, which is the area or region, it is simply made up of what? The magnetic field lines or the magnetic lines of what? Of flux. So the magnetic flux is represented by the symbol. We're going to have this in our calculations as we are to move on. Whenever you're to represent the magnetic flux, you're going to use the letter or the symbol phi. Remember, these are your Greek alphabeticals that we are considering. So this is the representation that you're going to use for the magnetic flux, which is measured in what? In Webers. So this is measured in Webers. Like there's something they call these Webers. Like I don't know how do you pronounce that one, but I mean I just call it like Webers, like WB in short, for the magnetic flux. So in this presentation that I'm showing you here, this is our permanent magnet, the one that we are seeing on our diagram. So let's just try to put this way. So this is simply an indication of the permanent magnet, which is the bar magnet that we are seeing. And these lines, as I was presenting, are the magnetic lines of flux, which are the magnetic field lines. So they are talking of what? The magnetic field lines. That is the concept that we are having there, the magnetic field lines. Or they are referred as the magnetic lines of what? Of flux. So there's nothing that much that you need to know there. Maybe you're just going to also need to consider the properties of the magnetic lines of flux that we had, because they also might ask that the properties. All right. So let us just consider also the properties of what? Magnetic lines of flux. What is it that we are supposed to consider as the properties by just being given this is something about a magnet, guys, that we might even not know. But what is it that is supposed to be considered? The magnetic lines of flux always flow from the north pole of a magnet to the south pole. This is the presentation that we are seeing here, taken from what? From the north to the south, from the north to the south. So that is the first property that you can actually consider as we saw it from that diagram. That is the magnetic. So you're going to consider the magnetic lines of flux. The magnetic lines of what? Of flux always. So this is the major part that you have to consider. They always flow. They always flow from the north pole. From the north pole of a magnet, from the north pole of a magnet to the south pole. To the south pole. So this has to be considered as a property of the magnetic lines of flux. Magnetic lines of flux always flow from the north pole of a magnet to the south pole. Also, the magnetic lines of flux always form closed loops, as we are seeing here, as they're going to form closed loops. So they always form closed loops. Form closed loops. It's another property that you need to consider there. They behave like stretched elastic bands, always trying to shorten themselves. So they behave. It's another property again that you must consider, like stretched. So it's gonna depend also the textbook that you're using, like stretched elastic bands. Though you remember, you see those elastic bands. So they behave like stretched elastic bands, trying to what? Always trying to shorten themselves. They're trying to shorten themselves in that manner. So that is always trying to shorten, always trying to shorten themselves, always trying to shorten themselves. So that is the condition of the magnetic lines of flux. They never intersect each other. These lines that you are seeing, these lines that we saw there, they will never intersect each other. No, they will actually maintain the movement that we are seeing from the north to the south. They will never intersect. So these ones, they will never intersect. They will never intersect. All right, so meaning to say, if we are given the magnetic lines of flux, consider that also the magnetic lines of flux that are parallel and flowing in the same direction will always repel each other if they are parallel. So if they are parallel, and flowing in the same direction, once they consider to be in the same direction, they will always repel. Okay? They will always repel. All right, so that is the consideration that you need each other. So meaning to say, if you are to consider that we have got a condition where a south has to be considered to a south, like this is your south, and it has to be taken to another south. Maybe it is a north, and you have to consider another north. There is going to be repelling. They are not going to attract these two. But once you consider a north and another one is a south, there will be an attraction there. Seeing north moving to the what? To the south, like attracted. That is the concept that you are going to actually have. So I want you to go through that and revise as much as you can, your theory and also the types of magnets. They can just ask you about that. Remember, Also, just you are to revise, just go through the types of magnets. They can ask you that. We've got different types, such as the natural types. We've got the permanent. We've got permanent magnets. We also have temporary magnets, such as electromagnet. These are also called electromagnets. The ones that are also referred to as temporary magnets. So let us try to just revise the basics there that we need in our revisions, theory, this and that, and also check your question papers. How are they going to be asking? Because this is a new part that we are going to be having or considering in our syllabus. And also try to go through the magnetic effects of electric currents as we consider the effects that will happen with the electric currents. What are the magnetic effects that can happen there? Considering the direction of magnetic flux, you need to just have the basics of that. All right, so we're just going to go through where we need to have the calculations sometimes that are needed on the magnetic flux density. They also need you to calculate, to be able to calculate what is referred to as the magnetic flux density. What is it that you are referring to considering the magnetic flux density? This is the amount of magnetic flux passing through a specific area. The amount, and remember we talked of magnetic flux previously, so now you've got an understanding of that. So it is the amount of magnetic flux, the amount of magnetic flux. Remember the symbol that I said, which is the phi. You're using phi like this. The amount that is passing through a specific area. Passing through a specific area. So it's passing through a specific area. So therefore, we can refer this magnetic flux density as B, which is equivalent to the flux over the area from the definition. So we are considering our flux density, magnetic flux density. And we are considering our magnetic flux there. Remember, that's your magnetic flux. As we saw previously, I said this magnetic flux is measured in Webers. The area being measured in square meters. So it means the magnetic flux density will be measured in what? That is Webers per square meter. Or this can be referred as the Teslas. Okay, they can write this as Teslas, which is T, is the unit of measurement of what? The flux density now. So given this, flux density can be calculated. Flux density can be calculated. And also, I need you to consider, you're going to look into examples. I also need to consider the force exerted on a current carrying conductor. That how do you calculate the force? Okay, that is the force exerted on a current carrying conductor. On a current carrying conductor. On a condition that it is placed inside a magnetic field. Placed inside a magnetic field. When it is placed inside the magnetic field, what will be the force that is exerted? So force can be calculated if we are given that consideration from the magnetic flux density times the length times the current. So you can have it times the current times the length, or length times current, no matter the way that you understand it. So in this case, we are referring to the magnitude of what? The magnitude of force that can be calculated. Remember our force being measured in what? In newtons, which you can just write as what? As N. Remember your force measured in what? In newtons. So you're talking about what? The force. The force. The force B, as we had this, guys, we say this is our magnetic flux density. So do not forget that we have to consider our magnetic flux density. This is our magnetic flux density. As we saw, it is measured in Tesla or the Webers per square meter. Talking of I there, which is what? The current flowing through the conductor. So there we are talking of what? The current flowing through the conductor. Current flowing through the conductor. So you'll be given that consideration of the current that is flowing through the conductor. Current flowing through the conductor. We also have to consider L, this one, which is representing the length. All right, so the current case, we do understand that this one is measured in what? The current is measured in amperes. Current is not going to change. Then our length of the conductor, then you have to consider the length of the conductor there. So this is your length of the conductor, which is taken in meters. So if you multiply the force, current, and the length, provided this is at 90 degrees, it will be, as it is placed inside the magnetic field, it will be perpendicular to the magnetic field. That is what? Perpendicular to the magnetic field. Perpendicular to the magnetic field. So that part actually is a concept which will affect when you are given, because this was supposed to be sine of theta like this. The formula, you're supposed to use it with the sine of theta, but when it is perpendicular, it is not going to affect that sine of theta. You won't see it because the sine of 90 degrees is equal to 1. So it is just like you're multiplying by 1. But you're supposed to have this formula here with a sine of theta, provided that it is not perpendicular. Maybe it is at 45 degrees or it is at another angle. Therefore, you're supposed to use, but in your syllabus, guys, they're just going to be working with that consideration being perpendicular. But unless stated otherwise, then you have to consider that. You have to consider the sine of what? The sine of the angle, which is the sine of theta. So this is the part which is important for you to understand as you are to consider the magnitude of that force. What is the magnitude? But in terms of the direction now, how are we going to see this direction of force? So in order for us to now consider this direction of force, the direction of force now, that is where we are going to use our Fleming's left-hand rule. Remember this left-hand rule. So it is the one that we are going to now consider in the determination of what? The direction of that force. So the Fleming's left-hand rule is associated with electric motors. As you are to consider it, it is associated with electric motors. So this is the one that we are now considering as the part of direction. As you are to consider the direction, to find the direction in which the force, this, which is the one that we just calculated there, apply Fleming's left-hand rule as follows. You're supposed to hold the thumb, first and the second fingers of your left hand. You're considering the left hand, remember, at what? At right angles. That is where I was considering to say at right angles, meaning to say sine of 9 to be equal to 1. So there's no effect there. So you have to consider as shown in this diagram. As you do that, point your first finger in the direction of the magnetic lines of flux. So your first finger is going to be representing the direction of the magnetic field, meaning to say the magnetic lines of flux, which are north to south. That is the concern of what? The first finger. And your second finger, what is it going to be? In the direction of what? Current, as you consider the second finger now. All right. Sorry for that. So this is The direction of what? Of current, as you consider the second thing. So that is the one that you have to consider there. The direction of the current, which is positive to negative. Your thumb will then point in the direction of the force exerted, which is that one that we're talking about. So the thumb now is the direction of force. So like I said, this is associated with what? Electric motors, and is sometimes referred to as the Fleming's motor rule. They can actually give it like that. It is associated with motors. So they can ask you to describe it. So you have to describe, like point your finger in the direction of the magnetic, your first finger, and that is, you have to describe from here. So also, as a consideration, before we look into our questions, please note that the direction of force can be reversed by either one of the following as you consider that direction of force that you're considering there. It can be reversed by what? By reversing the direction of the magnetic field. As the magnetic field is being reversed, we are reversing the force, the direction of force. We can reverse the direction of force by reversing the direction of the current through the conductor. By reversing the direction of current, it means the direction of force is affected. So the direction of magnetic field and that of current through the conductor affects. So like I said, we need to consider typical questions on what we just covered and see how these questions can be given. On this first example that we have, you are given that the magnetic flux density in the gap between two magnetic poles is 0.5 Tesla. So you're given the magnetic flux density. Remember, this is B from our presentation. So that is 0.5 T. For an air gap of area 575 square millimeters, you are given the area. Remember your area in square meters. So this is 575. How do you convert square millimeters to square meters? You multiply by 10 to the exponent of -6. Your area is in square meters. Square centimeters to square meters. How do you do that? You're simply going to multiply by 10 to the exponent of -4. Your answer will be in square meters. So that is, here we are given square millimeters times 10 to the exponent of -6. So we have our area. Then the question was, calculate the total magnetic flux. What is our total magnetic flux? From the formula that we saw in our presentation, I presented a formula which is representing the magnetic flux density. So what can we do with this? We simply have to make the magnetic flux the subject of the formula from that. Because we saw that the magnetic flux density is given by the formula that is the flux over the area. So simply make the flux the subject. This is same as over 1, so you can even cross multiply. That is 1 times flux. This flux is equal to B times A, that is BA. So meaning to say, by multiplying the magnetic flux density, which we are given as 0.5 times the area in square meters, which is 575 times 10 to the exponent of -6, you are going to obtain the magnetic flux in that case. So that was going to give us a that was going to be 0.0002875 Webers. Remember, this is WB4 Webers, which is your magnetic flux. And this can be given, or you can even write in milliwebers. You can even try to choose a number like you can 1, 2, 3, 4 here. You can also write as 2.875 times 10 to the exponent of -4 Webers. Okay, with the number of commas that you moved. Remember, you have a 0 digit, so it will be a negative exponent. You can choose to have it that way. This is magnetic flux. From what? From the magnetic flux density that you are given. So considering the other example that you're given, calculate the magnitude of the force exerted on a conductor. So we need to determine the magnitude of the force. And the conductor is what? 350 millimeters long. You are given the length of the conductor. 350 millimeters. Remember, milli times 10 to the exponent of -3. This is going to give us 0.35 meters, length in meters. Carrying a current of, you are given the current that it is carrying, that is 2.5 amps, and placed in a magnetic field of flux with a flux density of, we are given the magnetic flux density of 0.65 Tesla. What will be the force? So from our calculations, I say the force can be calculated as what? That is B times current times the length. Magnetic flux density times current times length, taken at right angles. So meaning to say the force was going to be determined. We have B, everything is there. So it's just substituting 0.65 times the current, which is 12.5, times the length. What is our length? In meters, the length in meters, that's 0.35. So you're going to obtain the force. So I want you to multiply this properly. You're going to obtain 2.8375 and so on, which is simply 2.844 to 3 decimal places. That's our force. Remember, force is measured or is to be taken in what? In newtons. So that is how the question was supposed to be like. We're done. Let's consider the third question. There's another question there we have to consider. Question number 3. Calculate the magnetic flux density when, okay, so according to the information that we have there, we need to calculate the magnetic flux density when 0.05 Webers is placed, which means we are given the flux of 0.05 Webers is spread over an area of, all right? So we're given the area which is direct to the square meters. So that's 1.6 times 10 to the exponent of -3 in square meters. And they want you to calculate the magnetic flux density. So this is a direct question, guys, because from our formula, you say this is equal to flux over area. So you simply have to substitute. We have the flux, we have the area in square meters. So that's 0.05 over the area, 1.6 times 10 to the exponent of -3. So you're going to obtain the value of the magnetic flux density. Remember, you can write this in Webers per square meter. You can write it as a Tesla like that. It's up to you, the way that you want to present. But the unit there, you can just write the Tesla. So it was going to be 31.25 Tesla or Webers per square meter. Just like that. So this was a direct question. Considering question number 4, you are given a conductor with an effective length of, so according to this information, the length is given 650 millimeters. In meters, divide by 1,000 or multiply by 10 to the exponent of -3. That was going to give us 0.65 meters at a velocity of. This is taken at a velocity in this case, all right? At a velocity, we are given, in this case, the velocity at right angles. All right, they're not given like, all right, there's another formula which uses the velocity, but there they are just saying at a constant velocity and at right angles to the, take note that part, at right angles to the magnetic field with a uniform magnetic flux density. They gave us the magnetic flux density, 0.04 Tesla there. Calculate the magnitude of force exerted on the conductor. So they want you to calculate the force when it carries a current of. So they gave us the current 10 amperes. So this was just a direct question also. Just like the previous case that we had at right angles, our force is going to be B times current times L, which is, we just have to substitute because we have these values. What is your B? Magnetic flux density, 0, thus we are given 0.04 times our current, which is 10 amps, times the length, which is 0.65. So with this, you're going to obtain your force. So the force, in this case, by multiplying these, you're going to obtain 0.26 newtons. Just like that. So you need to work with more questions. Just try to revise, also add up with your theory, depending with the textbook that you're using. So that is the part of theory that I do not want to add much, because your textbooks, you might be using another source which is explaining something or in another way. So please just work with the textbooks that you are having. Try to understand the concept, and after that, try to consider the question papers, especially the recent question papers. We have this part of our magnetism being introduced. So this is what you had, guys, till we meet again.